When the most massive stars die, they create the most extreme objects in the universe, black holes. So in this explainer, we're going to cover what they are, how they form, and their actual role in the cosmos.
First things first, we need to correct a very common misunderstanding. A black hole isn't an empty hole or some kind of puncture in the fabric of space. The reality is far more dense.
A black hole is a tremendous amount of matter that has been compressed into an extremely small area. This incredible density creates a gravitational field so powerful that it fundamentally changes the space around it. So how does this happen? The process begins when a star, one much larger than our own sun, runs out of nuclear fuel. Without the outward force from fusion, the star collapses under its own immense gravity, crushing its core into a single point. A black hole is really defined by two key components, and both of them challenge our everyday understanding of space and what an object is.
The first component is the event horizon. Now, this is not a physical surface, it's a boundary. At this boundary, the gravitational pull becomes so strong that nothing, not even light, can travel fast enough to escape. The nature of this boundary is absolute. Once anything crosses the event horizon, it cannot come back. This is precisely why black holes appear dark. Light itself is trapped there permanently.
At the very center lies the second component, the singularity. This is the theoretical point where all of the black hole's mass has collapsed. According to our current models, its density and gravity are infinite. And at the singularity, the known laws of physics cease to apply. The mathematical tools we use to describe the universe simply break down. We have no way of actually knowing what happens beyond this point. Now, the effects of a black hole aren't just confined to matter. Its immense gravity also warps the very fabric of space-time. According to Einstein's theory of general relativity, this is just what massive objects do. A black hole simply takes this principle to its absolute limit. So, near a black hole, time itself passes more slowly relative to the rest of the universe. This creates a strange paradox. From a safe distance, if you were watching an object fall into a black hole, you'd see it slow down as it approached the event horizon, eventually seeming to freeze in place, never quite crossing. For the object itself, however, the passage into the black hole would be instantaneous. So, given their destructive power, what is their role in the universe? It turns out black holes aren't just agents of destruction, they're actually fundamental to cosmic structure. We found that supermassive black holes are a standard feature of most large galaxies, including our own Milky Way. There is one right at its center. And these central black holes are enormous. The one at the center of our galaxy, Sagittarius A star, is over 4 million times the mass of our sun. Others out there in the universe can be billions of times more massive. So, black holes play a constructive role. Their immense gravity helps to shape the galaxy around them, dictating the orbits of stars and even influencing the conditions for star formation. Okay, so now we move from established science to the frontiers of physics. Black holes are natural laboratories for testing the limits of our theories, which leads to several unproven ideas. Some theories speculate that singularities could act as bridges or wormholes connecting distant parts of our universe, or maybe even connecting to other universes entirely. It is essential to be very clear about this. These concepts are purely theoretical. They emerge from the mathematics, yes, but there is currently no experimental evidence to support them. They remain active areas of scientific study. Another significant theory proposes that black holes are not eternal. Hawking radiation suggests that due to quantum effects near the event horizon, black holes slowly radiate energy away. Over immense timescales, this would cause them to shrink and eventually evaporate completely. So you see, black holes are more than just cosmic curiosities. They are the places where general relativity and quantum mechanics are pushed to their breaking points, forcing us to search for a deeper understanding of reality. And that conflict is our next topic. We're going to explore the fundamental disagreement between quantum physics and black holes, and what that might reveal about the nature of reality itself.